Welcome to another deep dive. Today we're going really small.
Yeah, like really, really small. We're talking about high dielectric stacks in microchips.
The tiny components that make our electronics tick.
Exactly. And we're looking into their reliability, or maybe I should say unreliability.
Oh, sounds ominous.
Well, it's all about this phenomenon called time-dependent dielectric breakdown, TDDB for short. We've got 3 pretty intense academic papers on this.
Okay, so before we get lost in the weeds, can you remind me what high-to-dielectrics are and why they even matter?
Right, so basically, chips are shrinking all the time.
Moore's law and all that.
Yep, exactly.
Yeah.
And we're cramming more and more transistors onto them. So the dielectric layers, the insulators in transistors, need to be incredibly thin.
Got it. But the problem is...
The problem is that traditional silicon dioxide, ION, can't be made thin enough without causing, well, leaks.
Leaks, like electricity leaking out.
Exactly. Leakage current. Waste energy, hurts performance, not good.
That's where the hike materials come in, right?
You got it. They have a higher dielectric constant,
Meaning
we can get the same insulating effect with thinner layers.
So thinner layers, smaller chips, better performance, all that good stuff.
You got it. But the question is, how long will these high stacks actually last?
That's what we're here to find out. So let's dive into the first paper. It talks about this interfacial layer. Sounds like a mouthful.
Yeah, the IL, basically high materials in the silicon. In a transistor, they don't always play nice together.
They need a mediator.
Exactly. The IL, it's an ultra-thin layer of silicon dioxide. It sits between the high material and the silicon.
A buffer zone, smoothing things over.
I like that, a buffer zone.
Oh.
And initially, many thought this IL being so thin would be the weak link. They thought it would determine the lifespan of the entire stack.
Makes sense. Thinnest part breaks first, right?
Right. And researchers were using these things called Weibull slopes to measure this, how consistently a material breaks down.
Man.
Well, early studies, they showed these shallow Weibull slopes seemed to confirm the IL theory. But then some researchers started testing larger areas of the dielectric stack,
Okay.
and they got different results.
Hold on. The size of the area they were testing mattered.
It did. In these larger areas, the Weibull slope changed. It went from shallow to steeper.
So it wasn't just the IL, after all.
Right. Turns out the hike layer itself plays a big role.
Interesting. Tell me more. What were they missing about the hike layer?
Well, it may seem robust at first, but the hike layer material actually generates defects much faster than the IL.
So it's got a hidden flaw.
Sort of. It's like, imagine 2 runners in a race.
Okay, I'm listening.
The IL starts off slow and steady. The hike layer, it looks like it's taking off strong. But in a short race, the IL might give out first. Over a longer distance, though, the hike layer's faster defect generation, it catches up.
It's the tortoise and the hare, but for microchips.
Yeah, something like that. So the size of the area you test, it matters.
Okay, so the larger the area, the more likely the hike layer's weakness shows up. But how do they actually see this happening? We're talking nanoscale stuff here.
They use simulations,
Yeah,
kinetic Monte Carlo simulations, or KMC.
that sounds intense.
It is pretty cool. They basically create a virtual version of the high stack and let the defects play out.
A little digital drama unfolding.
Got it. It's a 3D grid representing the stack. And as the simulation runs, you see these tiny defects popping up.
And they pop up faster in the hike layer.
Much faster. Eventually, they form a path for the current to leak through. Boom, breakdown.
And this all ties back to the Weibull slopes.
Yep, exactly. Small areas, the breakdown path mostly goes through the IL, shallow slope. Larger areas, the whole stack gets involved, steeper slope.
So the KMC simulations confirmed it's not just the IL, the hike layer is a major player in breakdown too.
Exactly. And to make these stacks more reliable, we need to control those defects. But it gets even trickier because some defects are already there from the start.
Pre-existing defects, like before the chip even starts working. Tell me more about those.
So these pre-existing defects in the hike material, like ticking time bombs just waiting to go off, what causes them?
Well, one of the biggest culprits is oxygen vacancies.
Oxygen vacancies. Okay, explain that like I'm 5.
All right, picture the hike material structure like a perfect grid. Atoms all lined up nicely. An oxygen vacancy is like a missing piece in that grid. Where an oxygen atom should be, there's nothing. It creates a weak spot.
A weak spot that does what?
Well, it can trap electrons. And those trapped electrons, they can lead to all sorts of trouble, ultimately even breakdown.
So like a pothole on a highway messes up the smooth flow of traffic?
Exactly. Great analogy.
Does the type of hike material matter? Like, are some more prone to these vacancies than others?
Oh, absolutely. Hafnium-based dielectrics, those are pretty common in chips today. They're known to be susceptible to these vacancies.
So not all hike materials are created equal, reliability-wise. Not at all. And that's why researchers are always on the hunt for new materials. In trying to minimize these vacancies in the ones we already use, one thing they're doing is doping.
Doping, like they do with silicon. What's that involve?
Yeah, basically adding small amounts of other elements. It's like tweaking the recipe to make the material more stable, less likely to form those oxygen vacancies.
Giving it some extra support, so to speak.
Exactly. But it's not just about the material itself, right?
Yeah.
The manufacturing process matters too. How they deposit the hike layer, how they treat it, all of that can affect defect formation.
So many factors to juggle. Material, manufacturing, and then all these different defects. Makes my head spin.
It's complicated stuff. And there's another piece to the puzzle. One of the papers dives into the energy levels of those traps.
Traps, meaning those weak spots that nab the electrons.
Right. And the key point is, different defects have different energy levels. Some hold on to those electrons more tightly than others.
So some traps are stickier.
Perfect analogy. And here's the kicker. The research suggests that in high-key materials like hafnium oxide, the traps have shallower energy levels than in silicon dioxide.
So less sticky. Easier to escape from.
Actually, no. It's the opposite.
Wait, what?
I know, right? Material science can be counterintuitive. Shallower traps, they actually grab electrons more readily.
Huh. Didn't see that coming.
Yep, it's one of those curveballs. And it means that even a small number of these shallow traps, they can really impact the reliability of the whole stack. Big challenge for manufacturers.
It really makes you appreciate the insane amount of engineering that goes into these tiny chips. So we've got material properties, manufacturing, and then the behavior of these nanoscale defects all intertwined. Where does the research go from here? How do we actually make more reliable chips?
That's the big question, and that's what we'll dig into in part 3, moving from the science to the solutions.
Right. We've spent the last 2 parts going deep, like really deep, into the world of high dielectric stacks. But how do we actually use all this knowledge to make better, more reliable chips?
Well, that's the goal, right? And researchers are definitely working on it. One big focus is on better testing.
Makes sense. We need to see how these stacks hold up in the real world, not just in a lab.
Exactly. And remember how we talked about the limits of high-voltage testing?
Yeah, like zapping them till they break isn't exactly realistic.
Right. So researchers are moving towards low-voltage, long-term tests. More like how chips actually operate in our devices.
Simulating years of use, but in a much shorter time. So what are we learning from these long-term tests?
A lot, actually. We're getting a better picture of how these stacks degrade over time. It's not always a sudden breakdown. Sometimes it's more of a slow decline.
As those defects we talked about start to build up.
Exactly. And this data helps us build better models to predict the lifespan of chips more accurately.
So we can get a better idea of when those defects might start causing problems. Are there any specific examples of how this research is actually being used to develop new chips?
Oh yeah, definitely. One area is new materials and processing techniques.
Okay, like what?
Well, we talked about doping, but there's also entirely new types of hike materials being explored. Zirconium oxide, lanthanum oxide, things like that. They might offer even better performance and reliability than the hafnium-based ones we use now.
Always good to have options. What else is on the horizon?
Well, another exciting area is the interfacial layer.
Ah, right, the buffer zone.
Yep. Researchers are finding ways to make that interface smoother, less prone to defects. It's like giving the hike material a stronger foundation.
So the hike layer has a better starting point, less chance of those defects popping up. What about those super precise techniques like atomic layer deposition? Didn't we touch on that earlier?
We did. ALD.
Yeah.
Yeah, that's pretty amazing stuff.
Remind me how it works again?
Well, it's like building the hike layers, atom by atom, layer by layer.
Seriously, atom by atom.
Yep. Ultimate precision. It lets you create these incredibly thin, uniform layers. Way fewer defects.
That's mind-blowing. So all this research into hike dielectrics, it's really pushing the limits of what's possible.
Definitely. And it's all driven by that desire for more, more, more.
Yeah.
Moore's law, you know.
Right, cramming more transistors onto a chip every couple of years. It takes these kinds of breakthroughs to keep that going.
It does.
Well, I have to say, I'm coming away from this deep dive with a whole new appreciation for what goes into making these tiny chips. It's easy to forget how much science and engineering is packed into our devices.
Absolutely. It's been great talking about it with you. Hopefully our listeners are feeling the same way.
I hope so. And who knows what's next for high-dye dielectrics? But one thing is certain, that quest for more powerful, more reliable, more energy-efficient chips, it's not going away anytime soon.
It sure isn't.
Well, thanks for joining us for this deep dive. Until next time, keep exploring and keep those curious questions coming.